effort involving Solomon, Chaturvedi, Simon and myself from India, and our colleagues Marmo, Morandi and Elisa from Italy. This is some work we have been doing over the past few years. We are trying to explore in a simple-minded way the relationships between the somewhat old concept of non-classicality in quantum optics, which Professor Agarwal already referred to, and the actually older concept of entanglement, to which this conference is devoted. Since the concept of non-classicality may be a little bit unfamiliar to some members of this audience, especially the younger people, I will dwell on it to some extent. So this talk will cover some old ideas and then some new ones. The definition of classical and non-classical states of radiation, quantized radiation, are based on Sudarshan's 1963 discovery of the diagonal coherent state representation for density matrices for radiation. And I'll come to it in a short while. These definitions are actually based on a physically very well motivated convention which was referred to by Agarwal. Over the years, many of us, many workers, including some of us, have re-examined that work of Sudarshan. We have tried to find new proofs of the diagonal representation, discrete approximations, and so on. We have also looked at generalizations with very interesting group theoretical features, and I will describe that very briefly as I go along. So the concept of entangled states, so I repeat that this discovery of Sudarshan is from the year 1963. The concept of entangled states for composite quantum systems is, of course, even older. After all, exchange interactions, determinantal wave functions for fermion systems were known very early. Though everyone was surely aware of it, it seems that the earliest explicit mention of it is by Schrödinger in 1935, and it is this that this conference is celebrating. Both non-classicality and entanglement, when they are used in the context of radiation, can be of various types or they may occur at different levels. For entanglement, we will mainly be concerned with NPT type, that is, entanglement which is seen when a density matrix for a composite system becomes unphysical when you apply the partial transpose operation to half of the system, because it then loses positivity. Of course, another general way to see entanglement is via violation of some Bell-type inequality. So let me mention the general relationship between these two concepts, the concept of non-classicality and the concept of entanglement. The relationship is that entanglement requires or presupposes non-classicality. I find this a little bit disconcerting because half the audience cannot see what I am highlighting, so I may avoid using this. So, whereas a non-classical state may be entangled, it may not be entangled. So the connection is clear-cut in only one direction. Of course, non-classicality is meaningful even for states of a single mode of the radiation field, and I will focus on them in most of my talk. Of course, for entanglement to be meaningful, we have to deal with two modes of radiation, or three, and so on. So, we have these set theoretic inclusion relations for two modes of radiation or more. Well, let me at least once use this. NPT entangled states are a strict subset of entangled states, which in turn are a strict subset of non-classical states. With this background, we can ask two general questions. For each signature of non-classicality, and I will describe some of them in a little while, for each signature of non-classicality, what do we have to add, or how much further do we have to go to arrive at a related signature of NPT entanglement? So you can say this is an exploration of the border between entangled states and separable non-classical states. It is the border at this point. The second general question is, if you are given a non-classical state, but it is separable, are there natural physical processes which will preserve this distinction between classical and non-classical states based on the Sudarshan representation, but which are able to convert the separable into an entangled state at the NPT type? When I refer to natural physical processes of this type, what I have in mind is the use of passive beam splitters which act unitarily on the radiation field, and they mix the operators of the different modes in a well-defined manner. So let me begin with the definition of non-classical states, and as I said, I have included this for the benefit of younger people who were born after 1963, well after 1963. I will describe it for the case of a single mode radiation field. As you know, the photon annihilation, now the top cannot be seen. We'll have to do this. All right. For a single mode radiation field, we have the annihilation creation operators obeying the standard commutation relation. And then you have the familiar Fock states with definite photon numbers, the coherent states, which are eigenvectors of the annihilation operator, and the relationships between them. So as you all know, the Fock states form an orthonormal and a complete set. The coherent states, on the other hand, are non-orthogonal, and actually they form an over-complete set. So these are the basic relations, definitions, and connections between these two sets of states. Now, with this background, the Sudarshan diagonal representation says that any density matrix for the radiation field, any quantum state rho, can be expressed as an integral over the complex plane involving projections onto the coherent states. And what appears in this representation is a function phi. This is the notation originally used by Sudarshan. So it is a real weight function. So such a representation exists not only for every density matrix, more generally for any so-called Hilbert-Schmidt operator. But in general, what happens is that this weight function phi in the Sudarshan representation is a distribution and of a very singular kind. I would like to communicate to you how singular phi of z can become in principle. So let me just quote the following result, which is valid for any Hilbert-Schmidt operator A, in particular for any density matrix. So the statement is that the weight function in the diagonal representation of A is in general a distribution of a particular class characterized as follows. The Fourier transform of phi of z, which is a two-dimensional Fourier transform, defined in this way by an integration over the phase plane. In principle, it can be of the form the exponential of 1/4 tau squared plus sigma squared times a function which is called the y weight of the operator A, which is known to be a square integrable function over the plane. So this result shows you how singular phi could in principle be. Its Fourier transform could be a square integrable function over the plane multiplied by a diverging Gaussian factor, diverging exponential. So this is the reason why one has to treat this object a little carefully. In any case, the definition or the convention based on well-defined good physical reasons, the definition of the classical states versus the non-classical states is given in this way. If this weight function phi is pointwise non-negative, by convention we say the state is classical, but I call it quantum optical sense classical. If this condition is not satisfied, if phi becomes negative somewhere in the complex plane, you would say that the state is non-classical in the sense of quantum optics. So this is the basic definition. As I say, it goes back, started in 1963. Now I will limit myself entirely to the so-called photon number conserving states or phase invariant states, that is, states rho which preserve the photon number. Such states have a simpler diagonal representation. The integration reduces to a one-dimensional integral over the positive real numbers. All you need for the diagonal representation is, you can see, the phase angle average form of the earlier phi, and this is usually written as P of I. So for such a state, conserving photon number, here is the Sudarshan representation, and this function P of the real positive variable I plays the role of phi. The interesting thing, well known, is that this function is directly connected to the probabilities for finding various numbers of photons in the state rho, something called the PND, the photon number distribution. And these expressions here show you the relationships involved. So since we have a phase invariant state, all that is relevant for the construction of rho is the set of photon probabilities P of n. They are obtainable from P of I essentially as moments with the n factorial in the denominator, and rho itself can be reconstructed directly. So for this class of states, clearly the definition of being classical versus non-classical in the sense of quantum optics is expressed in terms of this function capital P of I. If P of I is pointwise non-negative, we would say rho is classical. If this condition is not obeyed, we would say it is non-classical. So one should appreciate that this division into two families of states, these definitions are stated in terms of the pointwise properties of this function P of I. As a result, in these definitions, all the probabilities P of n for all photon numbers n are involved. I will describe these conditions in more detail in a short while, but I would like to introduce very briefly at this point a much simpler, sufficient condition for a state to be non-classical. A condition which is more than 20 years old, very well known in the quantum optics community, called the Mandel criterion or the Mandel condition for a state of radiation to be non-classical. The reason why this is useful is that it involves not all the properties of the photon number probabilities, but only the lowest non-trivial moments. And I include it at this point for two reasons. One, to give a little added insight into the notion of non-classicality, and secondly, because it will be used in a later talk in this conference. So how is this criterion set up? For a photon number conserving state, determined by the photon number probabilities, we set up a 2 by 2 matrix called the Mandel matrix. It has 1 to begin with, then the average photon number in the 2 off-diagonal positions, and down here it is the expectation value of A dagger squared, A squared. This differs from n squared because of the non-commutativity, and so if you write it out in terms of the photon number operator, it has this structure. 1 average photon number, down here average photon number, and here n squared average minus n average. So when you take the determinant of this 2 by 2 matrix, what you get is very simple algebra. You get the fluctuation in photon number minus the mean. If instead of A dagger squared, A squared here, in this lowest element of the matrix, we had the square of the photon number, n squared itself, this piece would have not been there, and then the determinant would have been always non-negative. Here, it can have both signs. Because we have subtracted the mean photon number, we get something much more interesting. So, what is the Mandel criterion for a state to be non-classical? As I say, it is a sufficient condition. If a given state is known to be classical according to the Sudarshan representation, automatically the Mandel matrix is positive semi-definite. The fluctuation in photon number is greater than the mean, and one says that the photon distribution is super Poissonian. On the other hand, if one finds that the Mandel matrix for a certain state is not positive, that is, if one finds fluctuation less than the mean, it is sufficient, it is a sufficient condition, it is a proof of rho being non-classical. The sense in which this is a one-way, much weaker statement than before is that you can have very well construct very easily non-classical states which, however, have positive Mandel parameters. So this is a much weaker condition to discriminate between the two possibilities, but it is very useful because it involves much less information than is contained in the entire photon number distribution. Now, I want to, at this point, digress a little bit. The operator diagonal representation of Sudarshan, as I have told you, has led to this notion of quantum optical non-classicality. A priori, it may appear to you that this is a very special or a very singular representation relevant only for states of radiation. While in some respects it is so, it may be useful to indicate that the concept of the coherent state and the idea of the operator diagonal representation are both much more general validity. And so I will spend a few minutes and make a digression and describe the situation, at least in qualitative terms and very, very briefly. There are two fruitful ways in which the concept of coherent states of radiation has been generalized. They lead, of course, to what are called generalized coherent states. One of these is due to Clauder and the other is due to Perelomov. They have both been known for quite a long time. The Clauder generalization of the concept of coherent states, it turns out, is very, very economical. It makes very few assumptions and it gives a very interesting definition. On the other hand, the Perelomov generalization of the coherent state idea has a rather intricate structure and it has very interesting features borrowed from group representation theory. And it is this that I will describe now. I will not deal with the Clauder definition. What are the ingredients for the Perelomov concept of generalized coherent states, you need the following: a Hilbert space H of some quantum system, a Lie group capital G relevant to the physical system, a unitary irreducible representation of that Lie group on that Hilbert space, and fourth, the choice of some fiducial vector, unit vector, in the Hilbert space. So you can see that the parallel of generalization of the coherent state concept is based on these four things: a Hilbert space, a Lie group, a unitary irreducible representation of the Lie group, and the choice of some standard or starting vector. Given these ingredients, the definition is the system of generalized coherent states, I repeat, in the parallel framework, consists of the set of all vectors psi which you obtain from psi 0 by group action. So you call it the set of vectors psi of G belonging to the orbit of the starting vector or the fiducial vector psi 0. So I can indicate it in this way: the orbit of psi 0 consists of every vector psi of G obtained from psi 0 by unitary group action. So you allow the group element to vary over capital G, you hold the vector psi 0 fixed. If you want to describe this family of states in terms of density operators, that can also be done. You easily define the orbit of the density operator rho 0 to be the result of conjugation by the group representation. I am concerned here only with the case where G is a compact Lie group, and in that case the Hilbert space, the representation U of G are both finite dimensional. Then it turns out that the so-called resolution of the identity, exactly as it holds for the ordinary coherent states of radiation, holds even in this framework, and it is a reflection of the Schur lemma. It is very easy to show. In the case where this group G is SU2 and the fiducial vector psi 0 is taken to be what is called the highest rate state or state of maximum magnetic quantum number, you get the well-known atomic coherent states which were studied by Agarwal, I don't know, 30 years ago or so. One can consider other choices of this vector psi 0, one can consider other groups G like SU3 and so on, and they lead to interesting families of generalized coherent states. Now the connection to the Sudarshan representation is the following. One can ask an interesting question. Are there necessary and sufficient conditions that we can write down which will guarantee that every operator capital A of interest to us in this framework can be written as an integral over projections onto these coherent states, generalized coherent states? And the situation is that such conditions can easily be derived, and you then find that there are many cases where the conditions are obeyed. Equally well, there are not very complicated situations where this representation may not hold. So I just want to mention that these conditions arise by using what is called the reciprocity theorem of group representation theory, coming from induced representations of groups and some amount of Gordon algebra. So the reason why I have mentioned this is just to say that the Sudarshan representation is not such an isolated result. There are similar results in a slightly generalized framework. One can use these results, go back to the case of the radiation field where the group G is the so-called Heisenberg-Weil group, and you then find some interesting additional results which are not useful in quantum optics, but they are worth knowing anyway. One is that whatever choice you make for this fiducial vector psi 0, the resolution of the identity always holds. And this is a property relevant to this particular group, the Heisenberg-Weil group. Even though it is a non-compact group, this result always holds. The other thing is that apart from the resolution of the identity, when do we have the diagonal representation, the Sudarshan-like representation for all operators? There is a clear statement, a necessary and sufficient condition for the existence of the diagonal representation, and this is that condition. I will not go into details. I only want to emphasize the clear-cut question with a clear-cut answer. Now I return to the examination of radiation field states. And ask the following question. Well, I asked two questions right at the start. So first I start by answering one of them. The earlier definition of non-classical states for single-mode radiation field was in terms of the diagonal Sudarshan representation. And as I have explained, that representation is completely determined by, or can be expressed entirely in terms of the photon number probabilities. So now one can ask the question, in terms of photon number probabilities, what are the necessary and sufficient conditions for a state to be non-classical in the sense of quantum optics? There is a very nice classical answer to this question, and this comes from the classical theory of moments, and that part of the classical theory of moments which deals with what is called the Stieltjes moment problem. Did I pronounce it correctly? I hope so. What you do is that you introduce from the probabilities P of n, auxiliary quantities Q defined with an extra n factorial. With the help of these Q of n, you build two infinite dimensional matrices. We call them L and L tilde. They are real symmetric matrices. The matrix L has at position n prime n, the element Q n prime plus n. The matrix L tilde, which is also real symmetric and infinite dimensional, has at that position n prime n, the element Q n prime plus n plus 1. So you can appreciate that these are distinct matrices. For example, the diagonal elements of L are all those Q's with the even subscript, whereas L tilde has on the diagonal Q's with an odd subscript, total odd. So the definition of the solution to the moment problem, the Stieltjes moment problem, is the following. From these infinite dimensional matrices L and L tilde, you build two sequences of finite dimensional matrices. Just take the part of L belonging to the first n rows and columns, and similarly from L tilde. So these are two sequences of finite dimensional real symmetric matrices. And here is the key result from the moment problem. The Sudarshan representation function, capital P of I, which we know is real, if it is pointwise non-negative, and that is when we would say that the state is classical, equally well the photon number distribution is classical. This happens when and only when every one of these matrices, capital L of n, capital L tilde of n, is non-negative. And this must hold for all dimensions, capital N equal to 0, 1, 2, all the way. On the other hand, P of I not being pointwise positive, which corresponds to the state being non-classical, happens exactly when one of these ln's and or one of these L tilde n's, or more than one, become indefinite. So the definition of classical and of non-classical 5 minutes, right? Convert exactly into statements about the sequence of matrices which are built up out of the photon number probabilities. This is the last sheet. Now, supposing that, well, as you know, for a single mode there is no meaning to entanglement, but suppose we couple this state of the mode A to another mode which can be either in the vacuum or in any coherent state, and you pass this special separable two-mode state through a beam splitter. Here, a beam splitter is a quantum mechanics, is a gadget described by an element of the unitary group in 2 dimensions, and it is represented on the two-mode Hilbert space by a unitary operator which has the standard actions on the annihilation operators and the creation operators of A and B. And of course, it is passive in the sense that it conserves the total photon number. So what you do now is you start with the single mode state, which may be classical, may be non-classical. Take the product with the second mode in any coherent state. So the result is, of course, separable. Pass this through such a gadget. A gadget which preserves this distinction between classical and non-classical states. So you get an output state. And then you apply the partial transpose operation to the output. And then you ask the following questions. When do you have entanglement of the NPT type? And I have essentially done. The result is the following. You have an exact correspondence. When the initial single mode state is non-classical in the old sense, which means by the moment theorem, some one of the L matrices or some one of the L tilde matrices is indefinite. Exactly when that happens, you find that after the partial transpose for the output state, the result is unphysical. It is not positive, and which means that the output is NPT entangled. So this signatures of non-classicality coincide exactly in this situation with signatures of entanglement of the NPT type. So this is a fortunate situation, and it shows that such beam splitter action for non-trivial beam splitter can convert initial non-classicality, but of the separable kind, into entanglement. So we can say that for single modes of radiation in this class of states, namely phase invariant states, there is no gap between signatures of non-classicality and appearance of NPT entanglement in this manner in which you couple the single mode state to the second mode in a coherent state and then pass it to a beam splitter. So initial non-classicality always emerges as final entanglement of the NPT type. And this is so thanks to the theorems that are available from the classical theory of moments, and the classical source for results about the classical theory of moments is a book of 1943 by Showhat and Tamarkin, published by the American Mathematical Society. So this is where we learned all these results from and found that they match perfectly with the signatures of entanglement. For two modes or more, such moment theorems do not exist. There are no such results in the mathematical literature. So other methods have to be used to look at that problem. That will be discussed in a later talk in this conference by Professor Chaturvedi in his presentation. So I believe I have ended in time, and thank you very much.
Thank you. Question or comments? Well, maybe I should probably ask a question, but
you don't have to.
No. Okay. I don't feel coerced, but I wanted to ask a question.
Sure.
Obviously, when you use Sudarshan or allow the Sudarshan representation of some of us now, you prefer normal ordering of creation and manipulation operators. So why would that be beneficial to saying a symmetric ordering and Wigner representation?
Well, the answer to that question is contained in Professor Agarwal's talk. Most procedures for detecting or doing experiments with radiation involve absorption of photons. And therefore, the normal ordering prescription is the preferred one.
Okay, but if you go to two modes, for example, you take two-mode squeeze state, for example, and how we know it's entangled, it would have a positive Wigner representation, so it will show any non-classicality in the Wigner sense. How would it work with the Sudarshan representation?
This is, as I said in the start, it is based on a convention. It is whether it is one mode or two, any number, it is the normal ordering rule which is constantly used. So the definition of non-classicality, the distinction from classical states remains always the same, always based on the diagonal representation, coherent state representation.
Probably I don't know interpret between the chairman and the speaker.
Oh, sure.
I think the question, the chairman's question you answered probably to the first or second transparency. The diagonal weight function will be the Fourier transform of a Gaussian with the wrong signature.
Yeah.
So it won't exist as a, for the squeeze state, the diagonal weight function will not exist as an ordinary function. So it will not be a probability, even though the Wigner weight is a very high probability.
Right.
Does that answer your question?
I think so.
So it was there in the second transparent and
Well, to add to that, the Wigner function we know it may become negative, but it will never be greater than 1 in magnitude.
Okay.
That bound is there, it's very useful. But this function phi can be really very singular. And this is the reason why sometimes people say it doesn't exist. So what exists is partly a matter of the amount of singularity you are willing to permit.
So then I have one more question. What about the finite dimensional system? So for example, two qubits, defining coherent state in parallel of sense in terms of the displacement operator group action, that would be possible. And
yes.
Would that be a way? We know, for example, that for two qubits we have the even only statement which based on partial transposition, which tell whether the system is entangled or not. Can you construct Sudarshan representation for those particular cases?
So I'll answer it in two parts. The first is to emphasize that there are very straightforward, necessary and sufficient conditions for the representation to exist. There are very simple examples of a group and a representation and a choice of fiducial vector for which those conditions are not satisfied and the diagonal representation may not exist. And we have given examples. They are easy to construct. That's one thing. So, there is no such thing as the generic case. You cannot say in general the representation will exist. You cannot make that statement. The second part of the answer is to say whether one should base a distinction between what you would like to call classical and non-classical on such a representation is yet to be explored and to be examined. Since many times physically simple-minded situations, the representation itself may not exist. One has to look at it a little more carefully.
Okay.